Great. Thanks a lot, Pradeep. Hope I'm audible and clear. Thanks a lot for all the folks who are joining in. I hope the sessions will be informative to you. So who am I? My name is Jebu Ittiachen. I am the CTO at Obvious. I've been a developer for more than 2 decades. I've been building for Web 1, Web 2, and Web 3. So I have a pretty good context of the lay of the land, which is there out here, and the whole idea of what I'll be talking through here is giving you the fundamentals of the system. So the idea is when we talk about how to be a Web3 developer, it's not to get you up and running and get you started to be or make you an expert and writing smart contracts after the session. The idea is to give you what is involved in the in getting a system up and running on Web3. What are the nitty-gritties which is there? What are the things that you should watch out for and get you up and running, or give you pointers on what you should be looking at so that you can then deep dive into some of these areas as you feel free. So quick intro on what we do here at Obvious. We are building your Web3 passport. Essentially, it is a multi-chain wallet which allows you to collect to various blockchains and interact with them. You will understand the importance of a wallet as we go through the session also. Some items that we want to get out of the way. There is a POAP which is there that we will be pushing out. So we will show links towards the to get your claim your POAPs in the middle of the session and towards the end of the session. The session I have not timed it, so it might run a little over. In case it is really off, so we will probably break it and then do a follow-up session. And yeah, standard disclaimer, this is none of this is investment advice, and all the third-party links feel free to use it at your own risk. So what will we be covering here, right? So to set the context, what is Web3, what is involved over there, go a bit briefly over what cryptography and blockchain technology is, get a little deeper into what Ethereum, the blockchain is, give an overview of how smart contracts looks and feel like and how it is different from the normal programming that you might be doing, gave some idea of what the tooling which is there, which is involved, and how you would get into that, and lastly some gotchas and where you might trip and fall. Okay. So with that said, what is Web3 and what's so special and why the hype on Web3, right? So if you see, Web3 has been, the term Web3 was coined pretty long back. 2014 is when the term was first coined by Dr. Gavin Anderson, who was a co-founder of Ethereum. The concept there at that point of time was more the team itself, or the Ethereum team itself, was largely dismayed by the centralization that was happening in the ecosystem and the fact that everything was being controlled by large corporates. The whole ecosystem was trying to see whether we can make it in a more decentralized fashion. How can we give the control back to the users, right? So that was the whole idea of Ethereum. And probably a little later on down the line, there was a good Medium article which was posted, which defined Web3 as read, write, and own. So Web 1 was primarily read, Web 2 had read and write, and Web 3 had read, write, and own, right? And the key differentiating principles that were there were that it would be decentralized, in the sense that there is no single corporate or an entity which is looking at making the system working. It is completely permissionless, in the sense that people are, you are not asked to kind of verify yourself with some other systems to be let into this ecosystem. It has native payments which is there, so that you don't have to, or you can do value transfer on the network itself, and it's completely trustless, right? So you don't have to kind of make sure that this is something who I am looking out to, or is this some party that I can trust in the ecosystem to kind of work in this system. So the key differentiator is the ownership aspect, right? So is it that we didn't have ownership before in the Web 2 world? Of course not, right? So we definitely had ownership. Centralized entities were there. You could have the concept of an ownership which is there. But the problem there was it was completely built on trust. If you were looking at examples like your social networks or your banks, right, you had to go to a centralized entity and they had to approve your bank account. If it is there, you have to go through your verification process. Everything has to happen before you're let in or you're assigned a bank account number. Social network, it's completely dependent upon that centralized entity to kind of let you through and give you that access into that system, right? So what changes with Web3 and how is it that ownership comes about in a decentralized manner? How does it make it permissionless, right? So everything is built on a distributed ledger on a blockchain. So blockchain technology is the key enabler for this. And the whole concept of permissionless, trustless aspects are enabled by cryptographic proof of ownership. So if you look at things like GameFi, gaming, DeFi, all of these things, all that you require is a wallet and access to the internet. You are all set, right? And even for getting an access to a wallet, all that you need is to download the wallet software and you should be good to go, right? If people could stop scribbling on the board, that would be great. So distributed apps or DApps that you might have heard is the key factor which is there on Web3, right? So what are they? Or what is different from what was there before from a centralized applications? If you were to look at, probably I will bring up this picture which is there, which is comparing a Web2 architecture with the Web3 architecture, right? So what is different in Web2 and what is different, and how does Web3 differ? So if you see typically a Web3 application, everything, or this is very simplified representation of how a Web2 application would have looked like, where you have a front end which is there, you have a backend, and you have a database, everything is there. You could run a small setup on a single web server. Then as you start growing and scaling, all of these pieces will start distributing, but essentially all of these things are all that is required for a Web2. Now, on a Web3 application, what changes is that you have a front end which is there, which is serving an application. You have a signer or a wallet which is there, which is authorizing and doing cryptographic signatures. There is a provider, an RPC provider, which you essentially talk to do API calls into the backend. There is a virtual machine which is sitting there and which is executing a smart contracts. Then you have a parallel system which typically is indexing this data which is there on the blockchain, which typically are people like Graph. And you have the IPFS or the interplanetary file system, which is a distributed file system, which says essentially everything that is out here is kind of this whole Ethereum virtual machine that you see here is a big what would look like as a massive slave master slave architecture for a database, right? If you look at that, that is the way it would be there. You could read from any of the nodes, but if you want to write anything, you have to go through sending a transaction and getting that included in a block. That's how typically things work. So a quick overview of how things work with cryptography and blockchains. Two fundamental aspects of cryptography, right? One is hashing and the other one is the public-private key encryption mechanisms. So what is hashing? Essentially what a hash does, it's a computer algorithm which essentially takes a bunch of data and generates a signature of the data. So how would it typically look like? Maybe I could show. Just give me a minute. So this is a demo site which is there, which essentially shows you how things work. So essentially, this is content hashing which happens. If you see however long the data that I type in, a hash is generated, which is essentially a fixed size hash, right? So what that gives you is a content signature, and any single character in it changes, the entire hash changes. And you can quickly verify if the content is the same, comparing the hash which is generated by the data, and that data could be arbitrarily long. So it allows you to quickly identify mismatches. Collisions are possible, as in you could have the same content hash to the same different content hash to the same hash value. but it is pretty rare. You have various hashing algorithms. Ethereum, which is the one that we'll be discussing later on, uses something called KICAC 256, which is a variant of SHA-3 algorithm, which is a hashing algorithm. Right, so just keep a note of these, and then please feel free to we can get into it a little deeper, or feel free to read up on it at a later point of time at your convenience, right? So the other thing that we have is symmetric and asymmetric key for encryption. So what does encryption do? It's a way of kind of making sure that your data is concealed, or you have a way of hiding the information which is there while it's passed over public networks. You have two ways of doing this. You have an symmetric and asymmetric way. Symmetric is where the key that you're signing the encrypting with is shared to the other guy, and you encrypt and decrypt with the same key. Asymmetric keys are where you have a public and a private key. So you encrypt with your private key, and you have the public key which is published all over, and anybody can get your public key. They can decrypt the data and see what is it that you have sent off to them. So this becomes the basis of kind of proving your identity, right? So the whole public private key and digital signature, which we do. So digital signature essentially is a way of taking a hash of the message and then signing that hash to say what is it that you're sending across. The way that you verify a signature on the other side is you compute the hash, the same hash on the message that you sent, and you decrypt the earlier message that you got with the public key that you have, and verify that the hash that you computed and the hash that was sent is the same. So that's the kind of verification mechanism that signatures do. Now, Ethereum and Bitcoin use something called ECDSA signatures. The good or the difference with these signatures is that you don't need the public key upfront. You can retrieve the public key from the signed message itself. So it allows you to kind of, since you don't know where the message will be coming from, or anybody could be sending a message, it allows you to recover the public key, and then it knows that who is the sender of this particular message, which is there. Right. So a quick intro of blockchain. I'm sure that most of you would know, but just to set the context, it's an immutable collection of block of transactions which are backlinked. So essentially you have a bunch of transactions which are cryptographically verified. So each of the transactions would have been signed by a particular individual or authorized person. And that is included into a block, which is then the hash of that is included in the next block. So which is what a backlinking means. And these are then shared across multiple computers. So that's the massively distributed system, which then takes some and becomes the blockchain that we know of today. So what happened with Bitcoin when it came up about in the early days is that it caught on, and then multiple people started building variants of Bitcoin to do their own specific systems that they wanted to build, right? So Ethereum did one level up on top of that and said that why don't we make this a generalized version of a blockchain? So this is a clip from the Ethereum yellow paper. What it does is a generalized state machine on the blockchain paradigm, right? Do we have any questions till now? I've not been looking at the chat. Great. So let's probably continue. If there is any questions which is bothering you, feel free to kind of interrupt. So continuing on blockchain, right? So you have, when you're building distributed systems, I saw a lot of folks were there who were students who were there, and also some from the industry. So typically when you're looking at the Web2 architecture, you have distributed systems which you'll be familiar, which would be doing things like, you know, a database system like Cassandra, something which has, or a Kafka, which is there, which are all massively distributed systems. You have multiple nodes in there. They are what they are called crash fault tolerant, right? So if one system goes off, it is still able to function. A threshold of systems go down also, it's able to function properly. A blockchain system is, we want it to be Byzantine fault tolerant. What we mean by that is there's a Byzantine generalist problem. The poster there is that in a public network, you could have many adversaries. There is nothing is guaranteed. That's also a key differentiator between what a centralized and a decentralized public network is, because in a centralized system, you control everything. In a decentralized public network, nothing is in your control. You don't know who you're talking to. So blockchain systems are designed to be Byzantine fault tolerant, where even if you have some actors who might be trying to not cooperate with the way the network is supposed to be working, and the system can still tolerate some amount of these spurious actors in the system. Right, and how does that thing happen is all built into there are various ways in which these things are done. So they have various levels of how they can tolerate these faults. Another key factor that happens on blockchain system is what is known as a consensus algorithm. So that is when something is posted onto a blockchain, when a transaction is posted onto a blockchain, how does it make sure that, how does the entire system come to a steady consensus that this is the accepted block, or this is the accepted list of transactions in there? So Nakamoto consensus was the one which was introduced by Satoshi Nakamoto for Bitcoin. This is a bunch of things which does proof of work on a BFT network. You have now systems which are proof of stake, which essentially take out the work aspect and then substitute economic share to kind of say that I have my stake in this particular, in the healthiness of this particular system. So I should be able to validate a particular block. And then you have other systems which are also evolved, something like a DPoS, a proof of authority, proof of history, and those DPoS is delegated proof of stake, proof of authority, proof of history, etc. Right. Another key aspect, which is the difference between Bitcoin and Ethereum, is the UTXO and an account-based model, right? So UTXO is what Bitcoin uses. Account-based model is what Ethereum does. UTXO essentially is the concept of, think of it in terms of a wallet with hard cash, which is there, right? You have nodes which are there. A transaction that you would be doing when you want to say pay somebody 120 rupees or something, you could give them, and you have a 100 rupee note and you have 50 rupee note, you give them 150 rupees. What they give you back is 30 rupees back to you, right? So that's how a UTXO transaction works. People, if you could stop scribbling on that, it would really help. Yeah, thank you. So UTXO is where you are given, you spend, it's called unspent transaction output. That's what UTXO expands to. Bitcoin, what happens is you have some value which is there, you give it up to somebody, and whatever is the amount which is left is given back to you, right? So you have a bunch of UTXOs in your account, and whenever you want to send some value to the other end, you collate a bunch of UTXOs and send that over. In an account-based model, it's more like a bank account where against your account, there's a number which is maintained. Every transaction, you send the exact amount, whichever it's supposed to be, to the other person, right? Bitcoin has something called Bitcoin script, which is what is used to build the Bitcoin transactions. And Ethereum has an EVM-based model. So would be a good time to take a break, and then there's the POAP which is there. Feel free to scan it with your POAP app and then claim the POAP. I'll just leave it here for a minute. And if there's any questions that I can take at this point of time, feel free to ask.
Hey, thanks, Jebu. Good evening, friends. I think I see a bunch of folks asking questions on the Q&A using the chat. That's the right thing to do. I also see a few people trying to scribble on the screen using the annotations. Kindly don't do that, right? Because there are a whole lot of other people who see your annotations as well. Please don't do that. And if in case you continue to do that, we'll have no option but to remove you from the meeting. We don't want to do that. We want all of you to be here and learn with everyone else. Kindly maintain the decorum of the room. So Jebu, I think there are a bunch of questions in the Q&A. There's also a request from a few folks to go a bit slower Probably you could do that in the upcoming things.
Sure.
Maybe you can pick a few questions from the chat.
Yeah, the reason I was trying to go a bit fast is because I had enough content. I didn't want to overshoot it. So what I'll probably do is try to go a little slower, and then if I spill over really bad, I'll probably break it, and then we'll do a full-on session later on. So I see a question there on what is the difference between proof of work, proof of stake, and proof of authority, right? So proof of work systems like Bitcoin and Ethereum, what essentially they do is to mine a block. A block is essentially what in a blockchain system, you have to have blocks which are added into the entire ledger, right? So the ledger which is there, which is built across, which is having a bunch of transactions, which is there. You need a way to verify that this bunch of transactions are valid, and that whoever is proposing it is the right one, whom I can trust, which is right. So the way proof of work systems work is they expect you to solve a mathematical puzzle or a cryptographic puzzle. Bitcoin uses a way in which you're supposed to find out a hash in which the preceding 3 bytes are 0. So the first 3 bytes of the hash should be 0. That is what Bitcoin uses. Ethereum uses something known as ETH hash, which again is a little more complicated than what Bitcoin does. All of them, the intent is to spend some computing power. That's why it's called a proof of work. It spends some computing power to verify that you've done this computational complexity work, and you have the right to kind of propose a block to the system. Now, when you propose a block to the system, because you've expended this work and you have put in that effort to kind of, it's almost like a sweat equity, or that you have spent some effort in there. It's kind of your stake to propose that block. That block is then validated by others. If the block is not valid, of course, it will be rejected. But the idea is that you have spent some effort to kind of validate, verify the transaction. Proof of stake is the computation stuff is not involved. The idea is to make sure that you are aligned with the incentives which is required to kind of get this network up and running, right? So in this case, when Ethereum is one network which is now moving from a proof of work to a proof of stake kind of a system. What happens when Ethereum moves to proof of stake is it's the validator networks are each and every node which is going to propose blocks into this blockchain is expected to put up a stake of right now the amount required is 32 ETH. You're supposed to put that up as a stake. So you're putting up that much money. So each ETH is right now worth about $2,300, whatever that amount translates to. So you're putting up that much equity into the network, and that is kind of held on your behalf. So if you kind of propose bad blocks, or if you double sign, or those kind of bad behavior is detected, then your stake in the network is slashed. So both of these, the idea is to make sure that you are working towards the larger goal of making sure that the system is working properly. So proof of stake is something where you don't spend that much energy. Proof of work, the problem is that it is not, you spend a lot of electricity to kind of figure out that computational hash which you have to generate. Instead of doing that, you now move to a proof of stake system where it is much, the energy that is spent, I think some predictions were that it goes down by almost 90 to 95% is what it cuts down to on the Ethereum network. So it's a much more greener system to keep running. Proof of authority, proof of history, all of these, a little more variance on that, and I won't probably go in deeper. You can feel free to read up on that. So ECDSA signatures, how that works, probably it will be too difficult to cover up in this question, in this session itself. Again, the basic idea is that of a public-private key signature itself, but the major difference that I said is that you can recover the public key from the signature itself. And how most of this public and private key thing works is that curve that I showed you earlier, right? So this curve that you see here is the elliptical curve which is used, and each of these networks have their own curves on how they try to do the signature fitting. So based on that, they have the various parameters which they use, and that mathematical formula is what is used to compute the public and the private key. And Ethereum, if you see here, I pasted is here, the R, S, and the V values that is there is the signature which an Ethereum transaction uses to kind of denote the signature. The V is almost like because the curve there are it could either be on the positive or the negative side of the axis. It is used to denote which side of the axis it falls on. I think I'll keep it at that because otherwise it'll get a little more complicated. So let me go ahead. There's been otherwise I'm guessing that it'll run out of time. Ethereum and what is it that it did differently, right? So Ethereum, Bitcoin, when it came out, it was a very simple store of value, as you would call it. And even though it had a script, it was a very limited script. It was not Turing complete. So you could not do, so it didn't have a basic thing like a for loop, right? You could not do a loop to kind of compute over various instructions which is there. It had very simple instruction set, and I think the instruction set was very limited about, it was a single byte which is used to figure out what is the instruction which it was trying to execute. So it was very limited, and people were trying to do various models of that. What Ethereum did is it made it a generalized state machine. So what is a state machine? In a computing terms, a state machine essentially is where you start off in a particular state. That state essentially is what the data is that it's representing. It could be thought of as a key value pair. There's a bunch of key value pairs, which is the current state of it. You apply some changes to it and reaches a new state which is there, right? So that that is what essentially a in the highest level it could be. Now, what Ethereum does is it gives you something known as an EVM, which is a virtual machine, which is a Turing complete virtual machine, and a language on top of that, which is Solidity, and there are other variants that which compile into EVM. Solidity is the most commonly used. It allows you to do generic programming on top of a blockchain. So every time that you want to initiate something, you can trigger off a bunch of a deployed smart contract, which is what when you write a program and is deployed onto Ethereum virtual machine, what you take that out is called a smart contract, and it can execute the instructions which is there and there. Now, it is, as I said earlier, it's an account-based model. I'll come back to some of these aspects a little later. Let me cover a bunch of the other areas. So there are two types of accounts, which is an externally owned account and a contract account. An externally owned account is where there's private key and a public key pair which is associated with it, which is controlled by an external entity. So me as a user who is using the Ethereum network, I have a private key for my account. I can sign off transactions with my private key, and that can be validated by the network to be coming from the public key associated with the private key that I have, right? Then you have contract accounts. These are accounts which don't have a private key, so it cannot initiate transactions. This is a code which is deployed on the Ethereum virtual machine itself, and it allows for the instructions which are stored in the contract to be executed. Any either EOA or a smart contract account, these are the basic four things which the EVM keeps track of. The state essentially of an account is these four things: the N1s, the balance, the storage root, and the code hash. And so N1s essentially is the for an EOA account, it is a number of transactions that is started from your account. For a contract account, it's a number of contracts which have been created from the N1s, from the contract account itself. The balance essentially is the ETH balance which is there. So ETH is the native currency for Ethereum network. What is the balance of that is what is recorded in the balance. Storage root and code hash essentially the what is the state that is recorded in the contract itself. So the list of all the variables that that it has in its program, and the code hash is the code itself that is there. I'll reference it later in the talk to a smart contract and show you how these map. Was there something?
Okay. No, Jebu, I think you can continue. For folks who are not able to get the POPs, I think there are a limited number of them provisioned. So if you have attended the session today, we know who you are, and you will get that email probably sometime later this week. So don't worry about the POP. Listen to the session and continue the learning.
Okay. So what are the addresses that is there, right? So for an externally owned account, which is that is a hash of the public key. So again, a CAC hash of the public key is taken, and the last 32 bits of that is what I believe is taken, and that is what your public key becomes. For a contract account, the hash is derived from the person who created the smart contract, and the N1s of the creator at that point of time is what is used to create the hash, and that's what the creator account looks like. So there's this thing of how is the state now stored in the Ethereum virtual machine, right? So Ethereum uses something known as Merkle-Patricia tree. So for the computer science folks out there, you might have heard of the Patricia tree, which is a tree representation of the data itself. It allows you to kind of store in a compressed format. It's a lookup format for data. Then a Merkle tree essentially, or a hash tree, is something which allows you to store data and figure out that the leaf nodes are the ones which store the data, and the intermediate node stores a hash of the data which is there below, right? So it allows you to quickly compare if the hashes of two nodes are the same. It essentially means that all the data which is there below that is same. So that's what it means. So the storage that a smart contract does is it uses a mix of Patricia tree and a Merkle tree. It's called extended. It's Merkle-Patricia tree, and that uses an extension on top of Patricia. There are three types of nodes which is there. I'm guessing we'll send out the article, this presentation itself, so that you can go through these links which explains it more in detail. So how does the state now looks like? So as I said, each block which is there in the blockchain, this is how the block header looks like. You have a bunch of these attributes which are there. And there's a state root, the transaction root, and the receipt roots which are there. The state root essentially then comprises each accounts, what are the different things which are there in that particular account itself. So if you look at what is there in a particular account, you have the account, the balance which is there, and all the state which is there. You have transactions which are sent to that particular account or to that contract, which results in some state change which is there, which is then represented in the new state which happens in there. Right. So all of these accounts together is what makes up the entire global state, which is what Ethereum is keeping track of. Okay. So this is how the global state of Ethereum would now look like on a particular block itself. So you have the previous hash, you have the state root, you have the timestamp, the block number, and all these things. And each of them then have the account itself which is there, which internally then has the N1s, the balance, the code hash, the storage root, and all that. So why are we doing all this stuff? Again, as I said, the idea of when talking about how to be a Web3 developer is give you the fundamentals, how things are built on. Just writing off smart contracts and is probably not going to make you any better. If you understand the fundamentals, you get to know a lot more of how these things work internally. Go back to your basics and then figure out how these things work, right? So that's the idea of running through these basics before I even go into a smart contract. So again, all of these together make up the global state. The state is stored as a Merkle-Patricia tree. The tree itself could be stored on every node which is there in the network in various formats. Ethereum uses various clients. There is no standard, or like there are 3 or 4 of them which are well known. Get is the one which is most commonly used, and Parity is another one. Get internally uses something called LevelDB, which is a storage system from Google. Parity uses something called RocksDB, which is again something from Facebook. And so this is how the data is actually stored on disk on each of the node which runs Ethereum, the blockchain itself, right? So what are these transactions and how do they look like, right? So when
there's a question on chat that is there a constraint for generating addresses, like you mentioned earlier, that hash should contain 3 zeros?
No. So that constraint was on Bitcoin and how the proof of work concept works. Okay? So that is for proving that I have expended this much energy and I have solved a cryptographic puzzle to say that I have run through, and the only way to solve the cryptographic puzzle is to run through various iterations and then figure out this hash which has this 3 bytes, the leading 0 with the leading zeros, right? But this one is just for each of your accounts. And this is not related to any of that stuff. This is just, again, a plain hash of your account itself. So there is no limitations on that. You have a private key. There is a matching public key which is computed off that based on the ECDSA algorithm. And that public key is hashed, and that's how you get the address that you hold for your Ethereum account. There is nothing which mandates that it has to be a certain format or anything of that nature.
Like, hi, Jebu, I asked that question. Like you mentioned about like it will use that nonce and ones. How it will be used to generate the address?
Right. So that is for the contract accounts, right? So if you see, yes, when you're deploying a contract, so that is always deployed. A contract is always deployed from externally owned account. So it is not automatically created, correct? So when for deriving the address of this contract account, because I said contract account doesn't have a private key, so it doesn't have a public key. So I cannot take a hash of the public key. The way the contract account's address is computed is by taking a hash of the creator's address and the N1s of that particular creator at that point of time when he's deploying a transaction. What is the N1s that that address state is in? That is what is used to compute the address of the contract account. Does it clarify?
Yes, I got it. Thanks.
Okay. Anything else, Anshuman, that I should be looking at, or I can go ahead?
Looks good.
Great. So what are these transactions which are there, right? So every account that is there, you to make a state change, you have to send a transaction to the network. That transaction has to be mined and has to be included in the block so that the state machine can move forward and the state changes can happen. What does this contain? It contains who the message is. It's essentially it's a message. It's an encoded message. It contains who the recipient is. So if you see, this is a dump of the transaction that I've taken from the Ethereum network, which was a couple of days back. That the hash that you see, the cast, is a tool that I use, and the hash that you see is a transaction hash. This is the message which is sent off. The input that you see here, which is 0x, that essentially is a value transfer. And the second one that I've said, there's an input which is there, which contains a string of bytes. This identifies a message which is being sent to the contract or to the end of externally owned account. This is used to identify which function to call, what are the parameters to the function, etc. I will relate that to the smart contract when we come to that. One thing to note is that only an externally owned account can initiate transactions. So a contract account, because it doesn't have a private key and it cannot sign off any transaction, it cannot initiate a transaction. A transaction is always initiated by an externally owned account. So it has to always come from outside the network. You can then call into a smart contract. You can say that I want to call this particular function on a smart contract. That can internally then call any other smart contracts, but it can never initiate a transaction on its own. Okay, that's one key thing to keep in mind. So contracts can call other contracts, but it cannot initiate on its own. Great. So let's look at a smart contract. Like, so this is simple smart contract, which is that and what it does is it's written in Solidity. It's if you open up Remix, which is one of the web IDEs for Solidity, this is one of the smart contract which it starts off with as a sample. It creates something called as a storage contract. It has a number which is a U256. It has two functions, which is a store and a retrieve. A store takes a number. What it does, it takes a number and stores it in the storage, and retrieve returns that particular number to you. Now let's see how that works. So this is that transaction. Let me just reload that so that we can start off at the beginning. I hope you can see my screen, right? Anshuman or Aditya, if you
Yes,
could just...
Jebu, we can see the screen.
Okay, great. So this is a simple contract. What it does is it, as I said earlier, there's a number, there's a store, and a retrieve function. What I'm going to do now is I'm going to compile this smart contract. What it will do is translate this Solidity code into EVM bytecodes. Simple as that. So you can all go to remix.ethereum.org and you'll get the same thing. So you can try it out on your own. This has a built-in EVM inside the browser itself. So that's where it runs. So once I compile this, it shows a tick mark out here, and this is the built-in EVM. So you can pick which is the environment that I want. And this uses JavaScript VM with the London fork of Ethereum. It shows that this contract is compiled. I can deploy that out here. It then shows the deployed versions of it. It shows that these two functions are available, which I can call. Retrieve is a read function. So it's something, so on Ethereum itself, you have the validator nodes which are involved for processing transactions, and any other participant in that can process a read transaction. So you can send the read to any of the nodes, and that will give you back a value, because it's everybody has the blocks. It will give you the state as of the last block that it knows. So this retrieve function, when I do, what it does, it's a call to this particular smart contract and gives you the value. If you can see here, it returns a value of 250 U256 of 0. Now I call this, which is sends a transaction. You can see what is actually going on here. It shows you what the transaction is, what is being sent out here. This is a transaction that's similar to what I had pulled out earlier, from whom to whom, all of the stuff. It actually sends out the transaction. Now, when I do a retrieve, it gives me back the value that I had set out here, right? So that's the bare bones, simplest smart contract, which is there. Now, how did that kind of go into the EVM itself, right? So if you see this entire thing that is there, this contract is what translates into one account itself. That address that you saw out there, that deployed address, maybe I should just go back to the thing to kind of... The contract address that you see, this 0xD91 blah 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 39138 is the address that is there. And to your earlier question, this is the one that I get after deploying. So based on my address, which is 05B3 blah 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 EDDC4, and my N1s, I got this particular address, and the contract, the code hash, I get this particular address. That is the deployed address which is there. To that, I did these particular calls. Right, so this then is what this state translates to. This storage element itself, right, that U256 value which is there, that is what goes into the storage hash which is there. And this entire code which is there, which is translated into an EVM bytecode, is what is referred to in the code hash itself. So this is how a smart contract goes into the EVM and how the state is maintained. Every time you do a transaction on this, when the state changes, this part of the tree changes, and that's what is recorded. So this entire tree, or what portion of the tree changes, and this hash changes, and that's what is recorded by EVM in its entirety. Okay. Hope that gives some picture of what is involved in the entire transaction and how EVM behaves itself, right? So what I did is deploy it onto a local in-memory EVM on the browser itself, and it gave me all of those things itself. So jumping on to what we use on day-to-day stuff, right? So what is a fungible token and a non-fungible token? So an ERC20 standard is what is defined for fungible tokens. What it defines is an interface to say what are the functions which is required for a smart contract, which is an ERC20 or which should be treated as an ERC20. So it's pretty straightforward. It doesn't do anything much of a magic. It has pretty straightforward functions, which is like name, symbols, decimals, the total supply of how many coins that it can have, what is the balance of a particular address, transfer some coins from an address to a particular address, transfer from again, and what value it is, approve, and an allowance. So if you were to break this down, what happens here is that inside this contract, if you were to implement it, you will have a storage element, which is kind of holding what the balance of a particular account is. So if I were to then, if you were to look at a particular well-known ERC20, like if you were to take an USDT or a WETH, which are well-known ERC20 tokens, in that contract, if you were to look at, probably let me open up the, so this is Etherscan. Etherscan essentially is your block explorer for Ethereum. This is one of the tools which you should be using on a day-to-day basis if you're really interested in what is going on. I'm looking up the USDC contract. So what it shows me here is you can actually look in for the verified ones, you can actually look at the contract itself. I'll get into what a proxy is and so there are two ways of looking at a well-known contract. So if you were to look at the token representation, it gives you things like who the holders are. This essentially shows each account, what is the balance of the particular token. And if you were to look at the actual code itself from the contract side, you can actually see what the code is that's represented. So you see here, and there are variations of it, which is a proxy. And this is, I will cover this in the gotchas part of it. This is how a code is made upgradable itself. But a representation of the ERC20 is what you would see here, where so you can then do calls into this particular contract itself. You would essentially do as a read as a proxy to do things like what is the allowance, what is the balance of. These are the methods that an ERC20 expects. So these functions would be implemented on this contract, and you can talk all that directly from here. So good thing is that you don't need anything else. You can call it directly from here. You can probably do the transaction of a particular on the contract is deployed on Ethereum, you can directly pick up something. So let's pick this address itself, right? I can carry the blockchain right over here itself and see what the value is. So I just picked up the same things. It's not going to give me anything, but it's just to show you that how you can query out here. So you can feel free to do that. You can also go ahead and write a transaction. So the things like, allowances and transfer, all of these available on here itself. If you connect your wallet, you can now have the ability to do these transactions. I know some of these might be going over your head, so I won't get a little deeper into that. So what does the contract specify? It specifies a bunch of methods, and it also specifies something called as events. Now, events are very key in how contracts operate. What it does is, as part of every contract, as part of executing the logic, you can have the ability to emit events. These events can then be read by or observed by third parties to figure out what is happening, what are the state changes which happens, or what are the things, token transfers which happen, what are the allowances that somebody did. All of these can be tracked. So in the earlier, when we looked at the Web3 architecture, there was this graph system that was there on the left side, right? So what that does is look at all of these logs which are generated by each of the transactions is getting executed, and then kind of index the entire system to say, what is the balance of a particular account, or what is the state of a particular thing. It indexes that entire thing, and it allows me to then query that state directly from there without even going to the blockchain. So which is why in that architecture that you had earlier, it allowed the front end is also talking to the graph system, because graph system ingests all this data and kind of represents this entire blockchain in a very queryable fashion, or a query friendly fashion, so that you can show this data off. So this is a NFT token contract, or the interface which is there. Similar to the ERC20, this is ERC 721, which defines the standard for it. The couple of things which changes out here is there's something called as an owner of. It says it has fixed number of tokens which is there. It says for each token ID who's the owner of this particular token. Earlier, if you remember, we had something called decimals in the ERC20. One key thing to note here is that Solidity and EVM doesn't support floating point numbers. The way they represent everything is as whole numbers. And if you want to represent fractions, you are supposed to take care of the computing of the decimals. So for something like USDC or USDT, it has support for 6 decimals, something like a WETH, which is the Ethereum's wrapped version, has support for 18 decimal places. So you can have up to that much level of precision. The way it does that is it's stored as a whole number. In the contract code itself, you would have to manage how the decimals are maintained, divided by that particular thing, and then process it. So by default, it doesn't give you floating point support. You have something called as approvals. What happens over here is that each token, the way it is, because it's a smart contract, the state of who owns what token and how much tokens is all maintained in the smart contract itself. The way to spend these tokens, or the way another contract, you pass the value off to another contract, and another contract can take the balance off from you, is via something called as approvals. Which is why when you interact with any contract on with a DeFi contract, or with any NFT kind of thing for selling on OpenSea or those kind of transactions, you would be asked to do an approval of that thing. So what that gives is the ability for the DeFi protocol or the OpenSea contract itself to kind of access your tokens on your behalf. So this contract is supposed to store the state that, okay, I have approved the spending of this particular token by the contract which I have approved for. So it almost allows you to kind of give certain limits, and then that contract can then spend that up to that certain limit that you've approved in the contract that is there. Events is something which I talked about earlier. So all of these, so if you were to compare the events from an ERC20 and ERC721, both of them have transfer and approval. And this one also has transfer, approval, and approve for all. Let's probably look at how this might look like on the blockchain, right? Again, going back to our Etherscan. Let's look at a particular block. A bunch of transactions are there in this particular block. If you were to look at any particular transaction in the block, this is an approved transaction. Right, so that says that somebody has approved USDT for trade on Uniswap v3. Right, if you were to look into it, this is the approve method, which is the ERC20 token approve method. This is the log which is generated, which says that there was an approval event. The owner was this particular address, and the spender is this particular address, right? So this logs which is generated is something which anybody can look at and then kind of use this data to kind of index the data which is available on the chain. Okay. So quick break. I want to make sure that is there any questions that I should be looking at? Is this things understandable, or is it way over your head? Is this things is the speed okay?
Folks on the call who want to discuss, kindly raise your hand and we'll just unmute you, and then probably you can bring up your points or
Okay.
ask your question.
I see an interesting question which I didn't get to. What is gas fees, right? So good thing. Every transaction that you send, essentially there has to be some way of ordering these transactions, right? So how Ethereum does that is all of these transactions sent in, there's something called as a mempool where all of these transactions are held, and the miner, whenever after they compute the hash, which we talked about earlier with the proof of work, they figure out which all transactions to include. Now, how do I figure out which all transactions to include? They look at something called the gas, which is there. And how is this gas computed, right? So every byte code which is there has some amount of gas that it takes. So again, there is a read and a write portion. On the read transaction, there is no gas which is spent. So any read transaction, any read call that you do is free. Write transactions or the transactions that you send to the blockchain, where you sign and send it to the blockchain, are where you actually have to spend the gas. So for these, what the EVM does is it has a gas allowance for a particular gas allowances, which is that. How is that thing done? It has predefines in that for each opcode how much gas is expected. For example, something like a storage has a certain amount of gas which will take, a multiplication has a certain amount of gas. So those that way, so it's already preset. And the way it again is calculated is it has something called how much you're willing to pay per gas. What is the price that you're willing to pay? And the way the gas calculated is the entire how much of a gas that you take, all the opcodes that it executes as part of a transaction, it computes the total gas that is there, and it multiplies by the gas price that you're willing to pay, and then that is the gas price that you arrive at. Now, when the networks get busy, the way for you to get a transaction is by bidding for a higher gas. And so you say that I want to, my transaction is more important, so I am willing to pay more per gas unit. I'm willing to spend more, or I'm willing to pay you more. If so, please include this transaction. And the way the gas is accounted for, or how it's compensated for, is the miner gets a cut of this transaction. So this is again, I'll come into what an EIP 1559 version versus an earlier version is. I'm talking about the traditional transaction. The miner gets a full cut of whatever gas is spended on that particular transaction itself. So everything is going to the miner. So which is why the miners are incentivized to kind of pick whichever is the highest gas paying transactions and then include all of that into the block. Now, about I think 7 months earlier or something, or 6 months earlier, Ethereum introduced something called the IP 1559, where they changed the model in which how the gas spending and the gas model is computed, right? So I have something called as a base fee and the miner tip, which is there. So that is used to now compute, and the base fee is something which is set to probably depending upon the network conditions that keep varying. So depending upon the last block, how much amount was used, and the base fee keeps varying. That base fee is completely burnt. So whatever amount that you end up spending as part of the computation of the base fee, that is completely burnt, or that much ETH is taken out of the entire supply that is there. The rest, the miner tip, which is the portion of that particular thing, is what goes to the miner actually. Right? So that EIP 1559 after came in, it has stabilized the gas fees a bit. Or earlier, what used to happen was during these crazy NFT minting sessions, people used to bid like crazy, and the gas used to go up and down like crazy. With EIP 1559, it stabilized a bit, but it still keeps going really crazy at odd times. Yeah, IDE was remix. How contracts can other contracts, and why would you want to call? Okay, that's contract calling another contract is very straightforward. So in your Solidity code, you would have something like, you would reference the other contract and then call a particular function. Why would you want to do a contract call? Suppose I'm building something like a lending protocol, right? So in that, I want to say, I want to debit a particular token. I want to deposit USDT into a particular contract. The way to do that is I would send a deposit transaction to the, let's say, a lending protocol like Aave, that I would call a deposit method on that and tell that I want to deposit USDT tokens and say about 50 tokens of USDT. Now, that call will then cause Aave contract deposit function to be invoked, which would then internally call the ERC20 function call of USDC to say transfer from, right? So you would call from one contract to the other to say that now I want you to transfer this particular amount of USDC from the guy who initiated the transaction to the contract address. This is where the approval also comes in. If you have approved this particular Aave contract to spend that much amount of tokens, is when that contract will say you can go ahead with it. So this is a very bare bone case of why why a contract would call another contract, and I wanted to put it also in context with the approval method that we discussed earlier. But you can think of various other use cases where you would want to build on existing contracts and reuse the existing contracts which is already there in the system to kind of build more complex ecosystem, right? So as in everything, it's an entire ecosystem. It's a money Lego. You have basic building blocks, which the idea is that you reuse as much of the infrastructure as possible and then kind of start working with it, right? Okay, great. So let me jump back in. So the developer tooling remix I showed you. Oops. Open Zeppelin, smart contract templates. There is a good bunch of already pre-written contracts which is there. Like, for example, you can find excellent implementations of ERC20, ERC721, various other versions which is there already done by Open Zeppelin. You can take that as a starting point and start doing from there. You need not have to reinvent the entire wheel. Take these as base contracts. Solidity allows you to extend your it has an extension mechanism. You can all extend implement the interface and also extend the existing contract itself, so you can build on top of whatever is available. You have for your developer tooling for your entire ecosystem setup itself, something like a hard hat, truffle. These are local environments which is there. It gives you a complete developer tooling set for things like running a local blockchain, running a test network, running your test code itself, all of those kind of things available with something like hard hat and a truffle suit. It also allows you for tooling like deploying a contract, writing scripts for all of that stuff. So if you look into any of the existing contracts, you will see pretty much all of them will tie into one of these frameworks itself, either hard hat or truffle. And you would need to get familiar with those. Also call out to adapt tools and things like Forge. These are again, so the earlier screenshots that I had when I showed the transaction details, it was using a tool called Cast, which is part of the Forge utility set. These allows you to again have a lot of command line utilities for querying the blockchain, debugging the data which is there available, all of those kind of things. It also allows you to run VMs which you can run your test against. The good thing about something like Adapt Tools or Forge is that you can write a unit test in Solidity itself. Hard hat and Truffle, you would have to write your unit test in JavaScript, which is probably you would anyway have to do that because your the UI would have to be built in JavaScript. But Adapt Tools and Forge allows you to write your unit test in Solidity itself. And one shout out again, then that you have to write tests. Unfortunately, for those of you who are used to writing code in production environments, I know most of you gloss over writing test, but in this environment, test is very key. Please have 100% coverage of your code, because actual money is involved, and it is really imperative that you have good coverage of your code. Pradeep, it's already 8:15. Should we continue, or should we kind of break and come back again at a later point of time?
I think since we're like slightly over time, probably we can just summarize now and then follow through with another session. I believe there is much more thing that we need to talk, as well as there are a few other people who also want some of the basics. So we'll plan for another session as a follow-on for this.
Yeah, so I had a couple of more things which were there. One thing that I wanted to anyway call out is what is the big difference between what a Web 2 and a Web 3 world is, that right? The contracts that you deploy on the blockchain are immutable. So in the sense you deploy in your typical Web 2 coding environment, you would write your code, make that available. You would do a bug fix and keep on fixing. You would have release cycles after release cycles where you keep on changing the code, right? Unfortunately, in the Web3 world, it's almost like your hardware, which you ship out. Once it goes out, it is there. You cannot change that code. You have ways to do an upgrade, but it's very complicated, or it is complicated. OpenZeppelin, Hardhat, all of these provide you tools to kind of automate that process for you. The reason why it's complicated is because you cannot actually change the code which is deployed. It does the way it does that, it provides a wrapper. There is a proxy for it, which is why when you were looking at the USDC contract, there was a proxy which is there, and then there's the actual code which is there. So you have to deploy it in multiple levels. You have to be very careful of the storage structure which you use, because you cannot you have to provision for enough storage elements which is there. Otherwise, all of that will get overwritten. So you have to be really careful about how things happen, which is why test again. You have to be thoroughly sure that this is the one that you want to push. And once that is available, you cannot take it back. You can have checks and balances in place to kind of prevent actions with that particular contract itself, but be really careful about pushing things in there. So I'll just leave this POAP time, and then probably I don't know if we have enough POAPs to claim back again, but if it is available, please feel free to claim it. To quickly summarize what we have covered till now, the entire how does a Web 2 and a Web 3 architecture kind of look like from a very high level, how cryptography primitives make up the transactions that are sent through, and how does it fit into the blockchain world, how a simple smart contract looks like, how does it get translated into an Ethereum state, how does it get represented on the Ethereum state, when you do a transaction, how is it actually change the state and what happens internally. And then we also looked at some ways on how an ERC20, ERC720 was the most commonly used ones look like, right? So that was a broad overview. Feel free to dig into all of these concepts that we discussed. I know I went through at a very high level probably, and some of them might have flown away ahead. Unfortunately, with the time that we have and with the audience as distributed at this, it's impossible to kind of please everybody. So hopefully the session was of use to you. We will do a follow-up session on a Web3 Wednesdays follow-up session to cover a lot more of these aspects. If you could give feedback on what you would like to see covered, that will also help us in planning the follow-up sessions. Great. Yeah, so we do have a WhatsApp group. Feel free to join in. The QR code and the links are available out here, so feel free to join in. Thank you, Jebu. Hey friends, thank you for all of you who have pressed till the end. I hope this session was very helpful. There is a feedback email that was sent out. Please share your feedback so that we know how the whole session went. Also, feel free to write to us on Twitter. You see it's obvious tech, and then tell us how did you feel. Similarly, there is this WhatsApp group where we essentially have a very candid and open discussion. In case you have a few more thoughts, questions to share, kindly do use that WhatsApp group.
to get in touch with us. We got a bunch of feedback from today's session. We'll work on them and get it going for the follow-on session. The follow-on session date for that we will announce pretty soon. Please look for announcements on Twitter and WhatsApp channels.
Great. So just a quick clarification for people who don't know what POAP is. It's just a NFT which is there. You can go to poap.xyz to read a little bit about what POAP is, and there's an app which is there. So feel free to go ahead and claim that. The QR code for that is there here. I don't know if we have POAPs left, but feel free to claim that. BTC bleeding plunge. Sorry, I won't comment on the markets. It's probably the wrong day to talk about it. There's enough bloodbath on the market. I don't want to comment on it. So folks, unfortunately, who didn't get the POAPs, we will send out QR codes later. Unfortunately, we had only a limited edition of POAPs, so we will send it out in an email so that you can claim it at your leisure.
Thanks,
Great.
everyone.
Thanks a lot,
thanks,
folks.
Jebu. It was wonderful for you to share this knowledge with us today. Thank you for all the folks who joined in. We'll continue conversation on WhatsApp and Twitter. You have a fantastic evening.
Thank you. Bye-bye.